Today's lesson will be on speed and velocity. Average speed is the distance traveled divided by the elapsed time. Or simply distance divided by elapsed time is equal to the average speed. So what units would this have? Well, distance we know is measured in meters and time is measured in seconds, so average speed should be measured in meters per second. Here's an example. How far does a jogger run in 1.5 hours or 5,400 seconds if its average speed is 2.22 meters per second? Solving this for distance. Distance is equal to average speed times elapsed time. Putting the two numbers in with their units, we obtain an answer of 1,200 meters. Excuse me, 12,000 meters. If you look at this, is that the correct units? Well, we know distance should be measured in meters. If we take meters per second from average speed and times it by seconds, the 2 seconds cancel out, one on top, one on bottom, so it does indeed work correctly. Now, average velocity is the displacement divided by the elapsed time. This definition looks extremely similar to average speed. Let's look at the definition we had for average speed. Average speed is the distance traveled divided by the elapsed time. So they actually are very, very similar, except that average velocity deals in displacement and average speed deals in distance. Okay. So the equations will be the same pretty much, except now this is dealing with displacement instead of distance. So the average velocity would be equal to the change in displacement, or the displacement change in position, over the change in time. Here's an example. Andy Green in the car Thrust SSC set a world record of 341.1 meters per second in 1997. To establish such a record, the driver makes 2 runs through the course, one in each direction, to nullify wind effects. From the data, determine the average velocity in each run. Well, in the first case, on the one on top here, he started at this position, 0, and ended at a positive displacement of 1,609 meters. And that took 4.740 seconds. So this was a positive displacement. Then they turned around and went the other way. Now he started over here and ended up back where he started, so it had a negative displacement. And this took slightly less time. So if you were to calculate the two average velocities, the first one had an average velocity that was positive. The second one had an average velocity that was negative. Why negative? Well, because they were going the opposite direction that we called positive. Now, how is this different from average speed? If we were to do these as average speeds, they both would have been positive because there would be no such thing as a negative with speed. Okay, because speed doesn't take into account direction. Now, how did they come up with the average? Obviously, they added the 2 together and divided by 2. But they only took the absolute value of the negative one here. Okay. Let's think of it from another standpoint. Let's say you're running around a track, a 400-meter track. You can calculate your average speed by taking the 400 meters and divide it by the time it took you to travel it. Let's say you ran the 400 meters in 1 minute. So it would be 400 meters in 1 minute. But what would your average velocity be? It would be 0 because you started and ended at the same position. So it would be 0 divided by 1 meter. Okay. Let's look a little bit more at graphing to see if we can understand this, what these two terms mean and how displacement and velocity are related. All right. We know that velocity is change in position over change in time. So if we have a displacement in meters versus time in seconds on a graph, and we take the slope of this graph, the slope of this graph would be displacement over time, which is indeed velocity. But the question arises, is it a constant velocity? Well, we know it's a constant velocity only if it covers the same amount of displacement every unit of time. All right, so in this case, we covered 2 meters in 2 seconds, as shown by the little green triangle. There it goes. So it's covered the same amount of distance every unit of time because the little triangle stayed parallel to the line. So therefore, it does represent a constant velocity. All right, let's look at the idea of changing velocity. Once again, we have a displacement time graph. Is this a changing velocity? We can check it out. I'm going to use the same type of triangles. I'm going to draw one every 2 seconds. So in the first unit of time from 0 to 2 seconds, we only covered about 4 meters. In the second unit of time from 2 to 4 seconds, we covered a lot more. In the third, we even covered more. So we're not covering the same amount of displacement every unit of time. So we must be speeding up because we're covering more distance every unit of time, or more displacement every unit of time. All right, let's look at the same idea, but this time with a curve curving downwards. All right, using the same type of triangles, but this time every 5 seconds. In the first unit of time, we covered this much displacement. In the second, we covered this much, a little bit less, and even less. So we're covering less and less displacement every unit of time. So we must be slowing down. All right, what's happening here? We know that speed is change in position over change in time. So if we take the change in position, which is the final position minus the initial, and in this case, pick any position, 2 meters over 2 meters, it comes out the displacement of 0. So when the displacement is 0, then delta x over delta t would be 0. So therefore the speed's 0. What this is indicating is you just stayed at the same position over time. Okay? Excuse me. Let me try that again. All right. So what's happening here? This is a position versus time graph. What is happening along this axis here, or excuse me, this line here? Well, obviously it's a positive displacement. And if we look at just a small section of this, from here to here, we went up 400 meters over 200 seconds. So we had a positive velocity. Here, in section 2, we had no change in position, but a change in time. So obviously the guy was standing there. And the second or third position, you can see his position went actually down. He started at 800, ended at 4. So there's a displacement of negative 400 over 400 seconds. So it's a negative velocity. All right. Let's see if you understand what's going on. A little test, self-test for yourself. All right. There's 4 different lines drawn there. Okay. Take a moment, pause the video, and see if you can determine which line depicts what type of motion. All right, let's see if you got the answers right. All right, this light green line would mean a constant velocity because you're covering the same amount of distance every unit of time. This brown one would be slowing down because you're covering less distance every unit of time. This dark green is speeding up because you're covering more distance every unit of time. And the orange one would mean that you're at rest, you haven't moved. So hopefully you got those right. All right. We're talking about average speed and average velocity and the differences between the two. We looked at the idea of graphing. Now we're going to look at the idea of why average speed and average velocity sometimes isn't that useful. So here we got a car race. And here we go. And they're off. All right. They have the same average velocity. How do we know that? They started and ended at the same time and had the same starting and ending positions. So therefore, they had the same average velocity. But you really had no idea what was happening during that race. One was just hanging out there and didn't really take off until the last moment. One was going all over the place. So, average velocity doesn't really give us much information. It only gives a snapshot at the beginning and ending of a motion. In other words, the police don't really buy into the idea of using average speed as an excuse. Yeah, the police really don't care about what your average speed is during a trip. They are interested in what speed you're going at that particular instant. And that's what we're going to be looking at next. All right, up until this point, did you notice that the slope of all the triangles we made were actually the average velocity during that interval? So if we were looking at the interval between the initial position and the final position, that would give us the average speed over that amount of time, over the 6-second time interval. But that doesn't really tell us much about what's actually happening at the instant of P. So how can we find out what the speed is exactly at the instant of P? What we could do is actually make a smaller triangle. Okay? And as we get a smaller triangle, we get a better idea of what this velocity is. It's getting closer to what the velocity is at point P. But that may not be good enough. So what we could do is make a smaller triangle. And a smaller triangle. And now we're getting closer and closer to what the actual velocity is at point P. If we get to the point where the triangle is so small that delta t is approaching 0, basically what we're going to be doing is drawing a tangent line to point P. And that tangent line to point P is what's known as the instantaneous velocity. Another way of thinking of it is instantaneous velocity indicates how fast the car moves and the direction of motion in each instant of time. So how this is read is it's a change of position over the change in time as time approaches 0. As this gets so infinitely small, this ratio will become the instantaneous velocity.